An AI agent scanned exposed services, fetched public exploit code, and decided where to pivot. Then one ordinary file-sharing command exposed the operator's own keys, scripts, targets, and session logs. According to Unit 42, the agent had started a web server from the wrong folder. In the next 4 minutes, you will see the architecture behind that loop, why the autonomous attacks in the recovered session failed, how the operator exposed the operation, and 4 gates you can apply to a legitimate business agent. First, separate the agent from the model. Unit 42 describes a Telegram operator sending goals to Hermes agent. Hermes provided orchestration, messaging, skills, MCP integrations, and terminal access. DeepSeek supplied reasoning for target selection, vulnerability assessment, code generation, and decisions. Search, scanner, and terminal results flowed back to the model, which could narrow scope, retry, pivot, or stop. That feedback created an offensive autonomy loop. The recovered session began with exposed Langflow services. It checked versions, obtained public proof of concept material, and tested the conditions the exploit needed. When those conditions were missing, it did not keep hammering the same route. It surveyed 10 product families, ranked candidates by severity, internet footprint, and likely exploitability, then pivoted to N8N. Unit 42's evidence shows persistence and fast triage, not an AI inventing exploits from nowhere. Here is the correction that headlines can miss: neither recovered autonomous attempt succeeded. The Langflow targets lacked required exposure conditions. The N8N forms the agent found required authentication, while the vendor advisory says the vulnerable path depends on particular publicly reachable form workflows. Unit 42 reports successful impact in separate manual campaigns, not from these autonomous Langflow or N8N attempts. Then the direction reversed. A Telegram request started a Python file server from /home/worker. By default, that helper serves its current directory. Instead of publishing one clean bundle, it exposed the working environment, configurations, API keys, scripts, target lists, shell history, and Hermes session logs. The command behaved as designed. The inherited working directory was the security failure. Consider a defensive composite. A company has a Telegram-connected maintenance agent that gathers diagnostics. Someone asks it to share logs on port 8888. The safer workflow checks the sender against an Allowlist, launches a disposable isolated runtime, and mounts a fresh empty staging directory. It copies in only approved, secret scan files, restricts network paths, sets a short lifetime, and records the action. High-impact tools stay behind policy, and reusable credentials never sit in the working tree. Current Hermes documentation describes messaging allowlists, approvals, deny rules, and isolated backends. Its July release also added secret source and credential surface hardening. Those controls have trade-offs. Approvals slow unattended work, so a read-only monitor should not need the same policy as a terminal-enabled agent. Deny rules help with honest mistakes, but Hermes documentation says they are not containment against an adversarial process. A container with broad host mounts or credentials is still broad authority. Logs help investigators, but they also need access control, retention limits, and secret redaction. The recap is simple: who can ask, what can run, which files and secrets are reachable, and what conditions stop the action at the target. Use the Agent Authority audit in the description on your own deployment. For more Mechanism First explainers, subscribe and explore the WSQ cybersecurity and AI agent training links below.